Imagine compressing the mass of 100 billion suns into a region smaller than our solar system, not stacked side by side, not dispersed across a galaxy, but bound inside a single gravitational well, so deep that even light cannot climb back out. In 2012, astronomers analyzing deep space X-ray survey data from the Phoenix cluster encountered radiation levels that defied expectation. The cluster, located 5.8 billion light-years from Earth, was already known to be luminous. But at its center, the energy output was extreme, powerful enough to outshine entire galaxies. The signal demanded scrutiny. An international collaboration of astrophysicists re-examined the data using space-based X-ray observatories and radio interferometers capable of resolving structures across millions of light-years. They mapped enormous cavities in the surrounding plasma, voids carved by relativistic jets erupting from the cluster's core. They measured gas velocities spiraling inward. They modeled the luminosity of the accretion disk. Each method pointed to the same conclusion. At the heart of the Phoenix cluster sits a black hole with an estimated mass approaching 100 billion times that of our Sun. To grasp that scale, consider this. The black hole at the center of the Milky Way contains 4 million solar masses. Phoenix A exceeds it by a factor of 25,000. If our entire solar system were placed near its event horizon, planetary orbits would be destabilized long before crossing the boundary of no return. And this object existed when the universe was only half its present age. Under conventional models, black holes grow through steady accretion and mergers across billions of years. Even optimistic simulations struggle to produce an object of this magnitude within available cosmic time. The numbers approach theoretical limits. Phoenix A is not simply large, it represents a stress test for gravitational theory itself. Its energy output regulates the flow of matter across a cluster spanning millions of light-years. Its jets displace hot gas on galactic scales. Its gravitational pull shapes the evolution of entire stellar systems that orbit far beyond our own. When its light began traveling toward Earth, complex multicellular life had not yet emerged on our planet. That ancient radiation, now captured by detectors, carries evidence of a universe operating at extremes we are only beginning to quantify. The discovery forces a question that extends beyond measurement. If gravity can build something this immense, this early, what conditions in the young cosmos allowed such growth? To answer that, we must examine how black holes form, and whether Phoenix A followed the rules at all. There is a built-in speed limit in the universe. Black holes are not allowed to grow as fast as they want. As matter falls inward, it heats up and shines. That light pushes outward. Feed a black hole too quickly, and the radiation pushes the fuel away. Physicists call this the Eddington limit, a natural balance between gravity pulling in and light pushing out. Under that rule, even the most aggressive black holes should grow gradually. Over billions of years, they might reach a few billion times the mass of the Sun. Phoenix A is estimated to be nearly 100 billion suns. To understand how extreme that is, imagine stacking every star in the Milky Way, all 200 billion of them, and compressing half of that stellar population into a single point smaller than our solar system. That is the scale we are confronting. When researchers revisited the data after 2012, they were not looking for records. They were verifying energy measurements from the Phoenix cluster. X-ray telescopes measured the heat of surrounding gas. Radio arrays mapped enormous cavities carved by jets blasting from the center. By calculating how much power was required to inflate those cavities, scientists could estimate the mass driving the eruption. The numbers kept converging. Independent methods pointed toward the same result. The statistical confidence is effectively beyond 5 sigma, meaning the likelihood that this mass estimate is a random fluctuation is extraordinarily small. In plain terms, the measurement is almost certainly real. The problem is not whether Phoenix A exists. The problem is how it formed. At 5.8 billion light-years away, we see this object as it was when the universe was roughly half its current age. There simply was not much time available. Growing something this massive would require feeding near the maximum theoretical rate for billions of uninterrupted years, an unlikely scenario in the violent environment of a galaxy cluster. One possibility is that it began unusually large, collapsing directly from a gigantic cloud of gas before stars even had time to form. Another is that many already massive black holes merged together during repeated galactic collisions, building a gravitational giant step by step. Both ideas stretch current models. If Phoenix A truly reached this size under known physical laws, then gravity in the early universe may have operated with an efficiency we do not yet fully understand. That would mean our timeline of cosmic growth, from the first stars to the largest clusters, is missing a critical chapter. And just as scientists wrestled with how such a black hole could grow so large so early, another surprise emerged from the same system, because instead of shutting down its surroundings, this enormous engine of gravity appears to be igniting them. In Part 3, we explore the contradiction that makes Phoenix A even more extraordinary. A black hole is supposed to shut things down. That is the expectation written into decades of astrophysical modelling. When a supermassive black hole becomes active, it releases enormous energy into its surroundings. Gas heats up, cooling stops, star formation declines. The process is called feedback quenching, and it is considered one of the primary regulators of galaxy growth. But in 2012, as researchers continued analysing data from the Phoenix cluster, another anomaly emerged. Using infrared observations to measure stellar birth rates and X-ray data to track cooling gas, astronomers discovered that the central galaxy was forming stars at a rate of several hundred per year. For comparison, the Milky Way produces roughly 1 to 3 new stars annually. In a system dominated by one of the most powerful black holes ever measured, stars were igniting at nearly 100 times our galaxy's pace. The finding forced scientists to reconsider a core assumption. If the black hole's energy output was as extreme as measurements suggested, then surrounding gas should have been too hot to collapse into new suns. Yet infrared signatures indicated rapid star formation. Spectroscopic data confirmed that large quantities of gas were cooling and condensing in long filamentary structures around the cluster's core. The confidence in these measurements was high. Multiple observational channels converged on the same conclusion. The probability that the elevated star formation rate was a statistical anomaly is extremely low. The paradox became clear. Phoenix A was not simply consuming matter. It was embedded in an environment where matter continued to organize, collapse, and ignite. One possible explanation involves the black hole's jets. Radio images reveal enormous cavities, voids carved into the surrounding plasma by outflows traveling at near light speed. As these cavities expand, they push hot gas outward. Over time, that displaced gas can cool, fall back inward, and compress into dense regions capable of forming stars. In this scenario, the black hole does not merely suppress growth, it reshapes the environment in cycles, heating, displacing, cooling, and triggering collapse. It is a more dynamic system than previously assumed. The stakes are profound. If ultramassive black holes can both regulate and stimulate star formation, then the relationship between gravity and creation is more intricate than our simplified models suggest. The largest engines of destruction may also be architects of structure. Phoenix A challenges the idea that feedback is purely inhibitory. Instead, it hints at a gravitational ecosystem, one where energy release and stellar birth are entangled. And to understand how such a balance can persist, we must examine the environment surrounding this black hole in greater detail. Imagine air so hot that metal would not melt in it, it would vaporize. Now imagine that heat spread across millions of light years. That is the environment surrounding Phoenix A. The Phoenix cluster is not empty space. It is filled with gas, heated to tens of millions of degrees. At those temperatures, atoms move so violently that they emit powerful X-rays, which space telescopes began mapping in detail around 2012. What scientists saw was not calm structure, it was a glowing ocean of plasma, vast enough to swallow entire galaxies. At the center of that furnace sits Phoenix A. Under normal conditions, gas this hot cannot form stars. When particles move that fast, gravity cannot easily pull them together. It is like trying to build a snowball inside a blast furnace. In most galaxy clusters, active black holes keep the surrounding gas this hot, effectively shutting down star formation. But Phoenix does something unexpected. Despite the extreme heat, large amounts of gas are cooling. Observations show thousands of solar masses of material losing energy every year. As it cools, it flows inward along enormous filaments, streams of matter tens of thousands of light-years long, feeding the central galaxy and igniting new stars. At the same time, radio telescopes reveal two massive cavities carved into the hot gas by jets from the black hole. Each cavity is so large it could engulf a galaxy like our own. To create structures of that size requires energy equivalent to billions of supernova explosions. Think about that scale. One black hole is powerful enough to hollow out regions of space larger than entire galaxies, and yet the displaced gas eventually cools, falls back inward, and helps form new stars. It behaves less like a simple destroyer and more like a cosmic engine cycling heat and matter. The jets push gas away, the gas radiates energy and cools. Gravity pulls it back, the cycle repeats. This is not random chaos. It is a feedback loop operating across distances measured in millions of light years. The surprise is not that Phoenix A releases enormous energy. It is that the surrounding environment remains finely balanced despite it. If this balance can exist here, in one of the most extreme gravitational systems ever observed, then our simplified view of black holes as purely destructive forces is incomplete. Phoenix A sits inside a cosmic pressure cooker, yet from that pressure, structure continues to emerge. And to understand the full scale of its influence, we must now measure the true size of the engine itself. How large is something that weighs 100 billion suns? The number sounds abstract, almost mathematical. But gravity makes it physical. When astronomers refined the mass estimate of Phoenix A in the years following 2012, using X-ray pressure measurements and radio observations of jet-inflated cavities, they were not only calculating how heavy it was, they were calculating the size of the boundary where escape becomes impossible, the event horizon. General relativity provides the equation. Mass determines radius. For Phoenix A, that radius is estimated at roughly 300 billion kilometers. That is about 2,000 times the distance between Earth and the Sun. If this black hole replaced our Sun, its event horizon would stretch far beyond Pluto's orbit. Every planet, every asteroid, every comet would lie well inside the point of no return. Nothing within that sphere would circle peacefully. It would fall. Yet even this staggering radius is only the inner boundary of its influence. Radio telescopes reveal jets launched from the region around the event horizon, moving at nearly the speed of light. These jets extend across millions of light years, punching enormous cavities into the surrounding gas. Each cavity is so vast that a galaxy the size of the Milky Way could fit inside it. To carve out structures of that magnitude requires extraordinary power. Independent calculations of cavity volume and surrounding gas pressure show that the energy released rivals the combined output of hundreds of billions of stars. And this is not a brief explosion. It is sustained over millions of years. Multiple observational methods converge on this conclusion with high statistical confidence. The measurements agree. The structure is real. At this scale, Phoenix A is not simply a massive object sitting at the center of a galaxy. It is a gravitational engine shaping an entire cluster. Gas across intergalactic distances responds to its energy output. Cooling patterns, star formation cycles, and plasma dynamics all bear its imprint. When something reaches this magnitude, size becomes influence, and if gravity was capable of assembling such a structure when the universe was only half its present age, then the early cosmos may have been far more efficient at building extremes than we currently understand. Which raises a deeper question. Is Phoenix A an extraordinary exception, or a surviving example of a more common, more violent phase in cosmic history? One that has largely faded from view but left its architecture behind? The possibility is unsettling. What if Phoenix A is not an exception, but a survivor? When astronomers announced the extreme properties of the Phoenix cluster in 2012, the focus was on its mass and star formation paradox. But as theoretical physicists began comparing it with cosmological simulations, a broader implication emerged. Objects of this scale may represent relics of a more chaotic era, a time when gravity assembled structure with far greater intensity than we typically observe today. At a redshift of approximately 0.6, we see Phoenix A as it existed nearly 6 billion years ago. That period sits between the universe's violent youth and its more stable modern phase. Galaxy mergers were more frequent, gas reservoirs were denser, large-scale structure was still consolidating. Under such conditions, black hole growth could have proceeded differently. Several research groups modelling early cluster formation have suggested that dense proto-cluster environments may allow sustained inflows of cold gas along cosmic filaments. Instead of sporadic feeding, a central black hole could experience prolonged, high-efficiency accretion episodes. In simpler terms, gravity may have had access to a steadier supply of fuel than we see in most present-day galaxies. If that scenario holds, Phoenix A may not have grown against the rules. It may have grown under different ones. The stakes extend beyond a single object. The mass distribution of black holes informs our understanding of how galaxies assemble, how clusters stabilize, and how matter is redistributed across intergalactic space. If ultramassive black holes were more common in the past, then the thermal and structural history of the universe may carry their imprint. Yet observational surveys show that objects approaching 100 billion solar masses are exceedingly rare in the nearby universe. That rarity suggests either that such giants formed only under specific conditions, or that many have since quieted, becoming difficult to detect as their fuel supplies diminished. Phoenix A may therefore represent a transitional snapshot, not the beginning of black hole formation, not the end of cluster evolution, but a moment when gravitational amplification, star formation, and large-scale feedback operated at near maximum intensity. If so, studying this system is not merely about measuring a record holder, it is about reconstructing an era. To test that idea, astronomers must look beyond Phoenix itself, comparing it with other massive clusters across different epochs of cosmic time. Because only by mapping the population can we determine whether this gravitational giant stands alone, or whether it is part of a larger, hidden pattern still waiting to be revealed. Across the observable universe, gravity leaves patterns. The question is whether Phoenix A is a solitary anomaly, or part of a larger hidden population of extremes. Following the 2012 identification of the Phoenix cluster's extraordinary core, astronomical surveys intensified. Researchers began comparing its properties with other massive clusters observed through X-ray and radio campaigns. Institutions including NASA and the European Space Agency expanded archival analyses, searching for similar signatures, extreme cavity sizes, unusually high central luminosity, and evidence of sustained cooling flows. What emerged was a distribution curve with a steep drop at the high mass end. Supermassive black holes in the range of 1 to 10 billion solar masses are now well documented. A handful approach several tens of billions. But objects near 100 billion solar masses remain exceptionally rare within current detection limits. Statistically, Phoenix A occupies the extreme tail of the mass function. That rarity matters. In cosmology, outliers can signal either measurement error or incomplete theory. With Phoenix A's mass supported by independent observational methods and high statistical confidence, the likelihood of error appears minimal. That leaves interpretation. Large-scale simulations of structure formation suggest that only the densest cluster environments with sustained gas inflow along cosmic filaments could support growth at this magnitude. Even then, such conditions would need to persist for extended periods without disruptive depletion. The implication is subtle but significant. Phoenix A may represent the upper boundary of what gravity can assemble under known physics, a natural ceiling rather than an impossibility. If so, its existence constrains theoretical models. Any viable cosmological framework must be able to reproduce at least a small number of such ultramassive systems. At the same time, observational limitations remain. Beyond certain distances, resolution decreases. Dimmer, less active ultramassive black holes could escape detection entirely if their jets are quiet and their accretion subdued. This introduces uncertainty into population statistics. Are we seeing the rare survivors of an early cosmic phase, or merely the brightest examples of a broader, partially hidden class? The stakes extend beyond classification. The abundance of ultramassive black holes influences models of galaxy merger rates, intracluster heating, and the long-term thermodynamic evolution of large-scale structure. It affects how matter is redistributed across billions of light-years. Phoenix A stands at the edge of current surveys, measurable, extreme, and instructive. But to fully understand whether it is a boundary case or a representative of something larger, we must step back even further. Because the story of objects like Phoenix A is inseparable from the broader history of cosmic structure itself, from the first collapsed regions of dark matter to the largest clusters we observe today. And that history reaches deeper than any single black hole. Long before Phoenix A ignited its surrounding cluster, the universe itself was assembling its first architecture. To understand whether objects like this are rare accidents or natural consequences, astronomers must rewind far beyond 2012, beyond the Phoenix discovery, back to the first billion years after the Big Bang. In that early epoch, matter was not evenly distributed. Dark matter formed a vast cosmic web, invisible scaffolding stretching across intergalactic space. Gas flowed along these filaments, pooling at dense intersections where the first massive galaxies and clusters began to take shape. Modern cosmological simulations, developed by international collaborations over the past 2 decades, attempt to recreate this process. When researchers input the laws of gravity, thermodynamics, and cosmic expansion, structures resembling galaxy clusters emerge. Black holes form at their centers. They grow through accretion and mergers, but reproducing something on the scale of Phoenix A remains difficult. The simulations show that early clusters were richer in cold gas and experienced more frequent mergers than the present universe. Under such extreme conditions, black holes could experience prolonged feeding episodes, accelerating growth. Yet, even in high-resolution models, reaching 100 billion solar masses by mid-cosmic time pushes the upper limits of what gravity alone can accomplish. This tension elevates Phoenix A from a record holder to a test case. If simulations can be adjusted to produce similar ultramassive objects without violating established physics, then our understanding deepens. If not, then either rare environmental conditions amplified growth far beyond typical cases, or certain physical processes remain incomplete in our models. The stakes are structural. Black holes influence how galaxies evolve. Galaxies determine how clusters stabilize. Clusters shape the distribution of matter across billions of light years. A change at one level cascades through the entire hierarchy. Phoenix A may therefore encode information about the efficiency of early gravitational assembly, about how quickly matter could collapse, how long dense gas reservoirs persisted, and how feedback mechanisms regulated cosmic growth. It is not just a massive object, it is a boundary condition for cosmology. And as next-generation observatories begin probing deeper into high redshift clusters, astronomers are searching for patterns, for evidence that Phoenix A represents either the extreme end of a distribution or a glimpse into a once more common cosmic phase. Because if similar giants are discovered at even earlier epochs, then the timeline of black hole growth will require recalibration, and that recalibration would ripple backward, altering our picture of how the universe assembled its largest structures. The question is no longer only how Phoenix A formed, it is what its existence reveals about gravity's role in shaping everything that followed. To answer that, we must consider the ultimate implications, not just for clusters, but for the future evolution of such giants across cosmic time. There is a final scale to consider, not the size of Phoenix A, not the age of the cluster, but time itself. When astronomers confirmed the extreme mass and energy output of the Phoenix cluster's core in 2012, the focus was on how such a structure formed. Yet an equally profound question follows. What becomes of a black hole this massive over cosmic time? Black holes do not explode. They do not fade quickly. Once assembled, they persist. At nearly 100 billion solar masses, Phoenix A contains a gravitational reservoir so vast that even minimal accretion over billions of years will continue to increase its mass. As galaxies within the cluster interact and merge, additional matter will drift inward. Some of it will ignite in stars, some will spiral into the event horizon. Over trillions of years, As stellar formation slows and galaxies exhaust their hydrogen, Phoenix A will remain. Theoretical physics predicts that black holes emit Hawking radiation, a quantum process so slow that, for an object of this scale, evaporation would require timescales vastly exceeding the current age of the universe. The larger the black hole, the slower the decay. For something this massive, the evaporation timescale is not measured in billions of years. It is measured in numbers so large they approach the limits of meaningful comprehension. This means Phoenix A is not merely a structure of the past, it is a structure of the future. Long after the brightest galaxies in the cluster dim, long after star formation ceases and stellar remnants drift cold through expanding space, the black hole will continue to dominate its gravitational domain. It will sit at the center of a quieted cluster, influencing trajectories even in cosmic old age. The stakes extend beyond speculation. Understanding the life cycle of ultramassive black holes informs models of long-term cosmic evolution, from cluster dynamics to the ultimate thermodynamic fate of matter. Phoenix A represents an endpoint toward which gravitational systems evolve when unchecked by external disruption, and yet, even this is not the final boundary, because objects like Phoenix A challenge more than formation timelines or feedback models. They force us to confront the limits of knowledge itself, the fact that singularities remain hidden behind event horizons, forever beyond direct observation. We measure their influence, we infer their structure, but we cannot see inside. In the next and final chapter, we step back from the equations and consider what Phoenix A ultimately represents, not only as a physical object, but as a mirror reflecting the reach of human understanding. In 2012, a pattern in X-ray data forced astronomers to confront something immense. It was not an image in the traditional sense. It was a concentration of energy at the center of a distant cluster, 5.8 billion light-years away. From that signal, through spectroscopy, radio mapping, and gravitational modeling, scientists reconstructed the presence of an ultramassive black hole approaching 100 billion solar masses. That object is now known as Phoenix A. Over the course of careful measurement and independent verification, the statistical confidence of its mass rose beyond reasonable doubt. Cavities in surrounding plasma confirmed the scale of its jets. Cooling filaments revealed unexpected star formation. Each dataset strengthened the same conclusion. Gravity, under the right conditions, can assemble structures at the very edge of theoretical expectation. The discovery carries weight beyond numbers. Phoenix A tests our equations of black hole growth. It challenges simplified models of feedback. It suggests that the early universe may have allowed matter to organize with an efficiency we are only beginning to quantify, and it demonstrates that even today, cosmic structure operates on scales that stretch the limits of comprehension. Yet for all its mass and power, Phoenix A remains unseen in the most direct sense. Its singularity is hidden behind an event horizon. We infer its existence from the motion of gas, the glow of X-rays, and the imprint of jets across millions of light-years. This is how modern astrophysics works. We do not touch the object. We do not travel there. We assemble understanding from fragments of ancient light. The photons captured by detectors in orbit and on Earth began their journey long before human civilization existed. They arrive carrying encoded information about density, temperature, velocity, and gravity. From those faint signals, a portrait emerges, a gravitational engine capable of hollowing out galactic-scale cavities, a black hole large enough that our entire solar system would disappear inside its event horizon. A structure formed when the universe was only half its present age, yet destined to persist for durations far beyond it. Phoenix A stands as both an endpoint and a beginning, an endpoint of gravitational accumulation near the upper boundary of known black hole mass, and a beginning in the sense that its existence forces refinement. Every extreme object sharpens theory. Every anomaly narrows uncertainty. Every confirmed measurement strengthens the bridge between mathematics and reality. The stakes are not merely astronomical, they are philosophical. Because when we measure something this distant, this massive, and this ancient, we demonstrate that human curiosity can extend across billions of light years and billions of years of time. We remain small in scale, but not in reach. Phoenix A does not know it has been discovered, yet through it, we have mapped another edge of the cosmos, and in doing so, expanded the boundary of what we can understand.